This is, I suppose, the second video I'm making today on derivatives of inverse trigonometric functions. And the whole goal here is for you, or at least me, and then you watching me, to find the derivative of inverse trigonometric functions. You'll have to know how to use implicit differentiation in order for this to really work. So, y is equal to inverse sine of x. If we're going to figure out where this formula comes from, this derivative formula you can look up in a book, well, you're going to have to get rid of the inverse sine. So I would say, hey, the first thing we're going to do is take sine of both sides. So sine of inverse sine, let's assume we're just not going to pay attention to any possible domain restrictions, which in this direction there really aren't, in the other direction there would be. What do you end up with? You end up with sine of y is equal to, well, just x. And we went from, hey, I don't know how to find the derivative of inverse sine, which is still true, but we rearranged. We know the derivative of sine. We know the derivative of x, at least with respect to x is pretty easy. And we know implicit differentiation. So the derivative of sine of anything is, or sine of something, is going to be cosine of that same something. Our something is y, which has a rate of change dy dx. And the derivative of x with respect to x is just 1. So we want dy dx, and we'll just have to rearrange 1 over cosine of y. That's not a great derivative for the derivative of inverse sine of x. We expect, well, inverse sine of x to have a derivative involving the same input x. When I used to teach trigonometry directly, I would always say the same thing. If you get confused, draw a triangle, and if possible, draw a right triangle. So most people have memorized, hey, sine is opposite over hypotenuse. And so you can read this two different ways. What do we want to say? Well, in either case, this angle is called y. And y is equal to inverse sine of x. That actually says a lot. Y is an angle, and we can see that kind of right in here. Sine only takes angles as inputs. And what's the inverse sine of x mean? I think a good way to say that is, if you took sine, meaning you took the length of this side opposite, divided by the length of the hypotenuse, you would get x. And that's actually also said directly right here. Hey, sine of y is equal to x. If you took sine of this angle y, this side, over this hypotenuse, you would get x. And so how long is that side? Well, we don't know. You can use whatever you want. I'm going to use x and 1. Those seem to be the easiest. We could use other things. We could use 5x, and divided by the length of the hypotenuse 5, we would still get x. But you might as well go easy. And so now you need the Pythagorean Theorem to find this missing side length, because our job right now is to find cosine of that angle y. And that's going to be the square root of the hypotenuse squared, which is 1, minus that opposite side length x squared. And so we can actually just finish off dy over dx is 1 divided by, well, cosine of y is, well, this is my angle y, so the adjacent side, square root of 1 minus x squared, divided by the hypotenuse, and I can just ignore dividing by 1. Let's see that again. Almost the same idea, rolling through, hey, how do you find the derivative of inverse cosine of x? Well, I don't know, or I haven't looked that up, or I'm taking a quiz and forgot. So maybe I just take cosine of both sides to get rid of that inverse cosine, at which point, great, I have cosine of y. I can take the derivative of cosine. I know implicit differentiation. And I know the derivative of x with respect to x. So derivative of cosine is negative sine. And since this input is y, we multiply by its derivative dy dx. The derivative of x with respect to x is 1. Let's rearrange, because we want that derivative notation on the left, because that's really what our derivative is going to look like. Now, I should probably have negative sine of y down here, but I'm going to put the negative on top. That's where I think it looks best. Much like when I found the derivative of inverse sine, I don't expect the derivative of inverse cosine of x to have a y as the input. Let's draw another triangle. What's this angle called? We're going to call this angle y, which is the same thing as inverse cosine of x, meaning if we took cosine of that angle, the length of this adjacent leg divided by the length of the hypotenuse, we would get x. You can also again see that right here. Cosine of y gives us the ratio x, or x over 1 if you prefer. So we'll call this side length x, we'll call this side length 1, and this opposite side way over here, what's that going to be? Pythagorean Theorem is going to be this side squared added together is 1. And so my missing side length is 1 squared, or 1, minus x squared. So now we need to take sine of the angle y. And what do we get? Well, we get the length of this side opposite divided by this hypotenuse length. So we just get that square root of 1 minus x squared. Okay, very similar process for the derivative of inverse tangent. And I think you'll see as we go through each of these. I'm going to skip writing tangent of y is equal to tangent of inverse tangent of x, and I'm just going to write tangent of y is equal to x. I am taking tangent of both sides. In this case, we do have to worry about a little bit more about what x can and can't be, but we'll worry about that in derivative applications. The derivative of tangent is simply secant squared of that same input. Our input is y, another function, which has a rate of change dy dx, and the derivative of x is 1. Rearrange to solve for that derivative notation stuff, and wait a minute. We just get secant squared x. And I don't know why, I'm a fan there. We could definitely change that to cosine squared x instead of 1 divided by secant squared. I don't know, I always just think of the derivative of inverse tangent having 1 over some junk, so I'm going to keep it that same way. Hopefully we're getting good at drawing these triangles. There we go. We'll keep everything blue. This angle we are calling y, but now y is inverse tangent of x, meaning if we took tangent, the length of the opposite side from the angle, divided by the length of the hypotenuse, we would get x. So we're going to say x here, 1 there. And the hypotenuse is the square root of 1 plus x squared, or x squared plus 1 inside the square root. Who cares? Well, it's your call if you want to do secant or if you want to do cosine here and then the reciprocal. It'll end up being the same anyways. I don't know, my students were always trained by their pre-calculus teachers, hey, change everything to cosine, but start thinking about secant. Cosine would be the adjacent side divided by the hypotenuse, so secant would be the hypotenuse divided by the adjacent side length. And so dy dx is going to be 1 over the square root of 1 plus x squared. Well, we're squaring that secant value, so we might as well just say 1 over 1 plus x squared. Wait a minute. We squared a square root. Should we put that as the absolute value of 1 plus x squared? No, 1 plus x squared is always greater than or equal to 1 anyways, so the absolute value is a waste of effort, if not, well, kind of just a waste of effort. All right, so you will see as we get through all 6 of these inverse trigonometric derivatives, it's, unless you have a really good memory for detail, not a great plan to just memorize these. They're not used a ton, so when they come up, I think it's best to just be able to go through this process to find the derivative rather than have them memorized, because it's always, well, some division of 1 and another 1 and an x squared and some other junk. All right. Now, there's also a pattern, so maybe you can just memorize 3 of them instead of memorizing all 6. So maybe that's an option. So take secant of both sides, and we'll have secant of y, an ugly y, is equal to x. So the derivative of secant is, I'm having trouble with my pen today. Secant tangent of that same input. Our input is y, so we need chain rule derivative of y with respect to x. The derivative of x is y. So we solve for dy dx again. Maybe I'll just leave dy dx below itself. And that's going to be 1 over secant y tangent y. What's y? Well, y is something we need to get rid of. Well, part of this is actually pretty easy. Notice up top, I have secant of y. That's going to be a little weird in a second, but notice secant of y is equal to x. So that I can make the substitution, but tangent of y I can't, or at least not as easily. So I'm going to draw my triangle and fill in this angle as y is equal to inverse secant of x. Means, well, the adjacent side over the hypotenuse would be cosine. The hypotenuse over the adjacent side would be secant. And if I'm doing tangent, I'm doing tangent of that angle y. I would need the opposite side, which is going to be the square root of x squared minus 1. All right, so here we go. So dy over dx is going to be equal to 1 over, well, what's tangent of y? That's going to be the opposite side divided by 1, so just the square root of x squared minus 1. And secant of y is equal to x. Except we need absolute value on that x to keep the derivative, the instantaneous rate of change, correct, having the correct slope. Turns out inverse secant only ever has positive slopes. I think I have another video on that if you are interested. Or there are other videos on YouTube if you need. If you are guessing that there's a pattern, there is. This one you may not be able to guess, but once we get to the derivative of cotangent, maybe that pattern will be a little more clear. So cosecant of y is equal to x. The derivative of cosecant is negative cosecant. Cotangent of that same angle. The angle we have is y, so chain rule dy dx, and the derivative of x is 1. dy dx, do some algebra, is going to be negative 1. I really like having that negative up there. Cosecant y and cotangent y. Much like the last problem, I already have a cosecant y I can subtract, but I still need that other part, the cotangent of y. And so I'll draw my right triangle. Y, this angle, is inverse cosecant of x, which means cosecant is the reciprocal of sine. So sine would be opposite over the hypotenuse. Hypotenuse over the opposite side length is x, or the ratio x over 1. And this adjacent side length, which we're going to need for cotangent, is the square root of x squared minus 1. So let's see, dy dx. Cotangent y is going to be the adjacent side length divided by the hypotenuse. So just the square root of x squared minus 1. As very similar to the last one. And we already have a cosecant of y is equal to x. We'll make that replacement. And we also need some absolute value there on the x because inverse cosecant actually only has negative slopes everywhere. Negative instantaneous rates of change. Slope of the tangent line is always negative. All right, so that should look awfully similar to the derivative of inverse secant. And then, let's see, inverse cosine has a derivative very, very similar to the derivative of inverse sine. So do you have a guess as to the derivative of inverse tangent? I'm sorry, inverse cotangent. That'd be a really easy guess as to the derivative of inverse tangent when we were staring at the derivative of inverse tangent. So cotangent of y is equal to x. The derivative of cotangent is negative cosecant squared of that same input y, so chain rule, dy dx, and equal to 1. The derivative of x with respect to x is 1. dy dx is 1 over negative cosecant squared y. And I am going to need a triangle. So y, this angle, is the same as inverse cotangent of x. So that means the adjacent side length divided by the hypotenuse is the ratio x. And the hypotenuse is going to be the square root of 1 squared, or just 1, plus x squared. Now that we have all three sides inside that triangle, we can take cosecant of our angle y. Cosecant is the reciprocal of sine. Sine is opposite over hypotenuse, so cosecant is hypotenuse over the opposite side. So we get square root of 1 plus x squared, and we're squaring cosecant. Ooh. So I can just get rid of the square root and the square and just say 1 plus x squared in that denominator. Should we keep absolute values? Nope. 1 plus x squared is always greater than or equal